Okay, this is going to be one of the most important videos covering content that's really important in this chapter. Let's remember that hemoglobin has a function that is very complicated. It needs to bind oxygen tightly in the lungs where it picks up that oxygen, transport it to the tissues, and then bind it weakly so that it falls off. Now, we also said that hemoglobin's tetrahedral heterotetramer, alpha 2 beta 2 structure, is really what's going to allow it to do that. It's got 4 irons and it can bind 4 oxygens one at a time. Again, think of it like a taxi that can have 4 passengers in it. So let's go down to the bottom of the page and consider how this is going to work with the oxygen saturation curve. Let's put it down here like we did on the other page. This is the percent saturation from 0 to 100% for any particular molecule that we're interested in with regard to how much oxygen is bound. Let's put that down, percent oxygen saturation. Over here on the x-axis we have the PO2 in torr, and that goes from 0 to 100, coincidentally. And we also said that this is the muscles down in this area where there's not much oxygen, and this is the lungs. So what we have up here already is the myoglobin hyperbola that shows myoglobin binds oxygen simply. It's tucked way up in the upper left corner because it binds oxygen very well. Now, here's the critical part. What about hemoglobin? We're going to do that. We'll do it in green again. What should its curve look like? Well, we know this. If you have no oxygen, it can't have any saturation. And we know that if you go to very high oxygen concentrations, you're going to have 100% saturation. But here's the tough part. How can we draw a curve that is really tight binding to oxygen in the lungs, but not tight binding in the muscles? What we're going to have to do is draw a curve that has low saturation down here in the muscles because it doesn't bind it very tightly, and then tangent out again at high oxygen PO2s in the lungs. I want to tell you that this curve is not just different from myoglobin in the way it's shifted left and right, but it's also different in its shape. This is not a hyperbola, it's a sigmoidal curve. Sigmoidal comes from the Greek letter sigma for S. It's kind of S-shaped. Now, let me say it again, because this is the important part. The hemoglobin has high saturation out here in the lungs. I hope that makes sense, because let's think of this again as a transporter, like a taxi. If you're going to have good efficiency, you want every taxi to have as many passengers as possible. So if hemoglobin is a taxi, we want it to pick up 4, fully saturate itself, 4 oxygens, and then leave on its trip out into the tissues. However, when we get out into the tissues, into the muscles, we want the hemoglobin to give up its oxygen and become unsaturated. So that's the tricky part, is what we see down here is the result of the equilibration in the muscles. And that's a real key part. This is very difficult conceptual material, and we're going to cover it on multiple videos. Let's take a break for a second, and let's practice something we learned on the previous page. I want to ask you, what is the P50 for hemoglobin in the fashion that we've drawn it here on this page? Yours might be slightly different. So whatever your answer is, let's see how you do. What is the P50 for hemoglobin? And let me ask you this follow-up question. What does that say about the affinity of hemoglobin versus myoglobin? Does myoglobin bind tighter than hemoglobin, or does hemoglobin bind tighter than myoglobin? Let's see what you come up with. Pause for a moment. All right, determining P50 is really important. As we said on the previous page, to determine P50, you come down to the 50% saturation, you draw over to the line, green is our hemoglobin line, and then you draw down to here. And since this is about 0, 20, 40, I'm going to say maybe 35. Now, by the way, that's a pretty good answer, but it's not quite correct. I'd take off points if that was your total answer. The real answer is 35 torr. You got to have the units on there. Okay, what does that say about the affinity of hemoglobin for oxygen compared to the affinity of myoglobin for oxygen? The answer is that myoglobin is better than hemoglobin. Let me make sure you understand what I'm saying. I'm going to add something to this. The affinity for oxygen is greater for myoglobin than it is for hemoglobin. Now, that might strike you as odd, but think about it. We said in our little diagram of the circulation system that in the muscles, we want myoglobin to beat hemoglobin. We want to rig it so that myoglobin soaks oxygen in and hemoglobin gives it up. And that's really visible in this curve right here. Let me go down to about 20 torr, and I'm going to draw a line between these. This is a line that represents what's going on in the muscles. And what you can see is there's a large gap here. And what that means is written down at the bottom. Let's fill this in. The bigger the gap between curves, the more efficient the oxygen transfer. Isn't that what we want? We want oxygen to go from hemoglobin to myoglobin, and that's a big gap. Think of it this way. Like I said earlier, the difference between these is the result of the equilibration, or the competition, we might say, between hemoglobin and myoglobin for oxygen in the muscles. So what we have here is 90% saturated myoglobin and maybe 12% saturated hemoglobin. Think about that like the score of a football game after the game. If you looked at a football game and the score was 90-12, you would say the 90 score dominated and beat out the other 12 score. And that's what's happened here. After they fought over the oxygen, myoglobin won and is fully saturated, or almost fully saturated. Hemoglobin lost, gave up a lot of its oxygen, and so we ended up getting a great directional transfer. So the bigger the difference between the scores, so-called scores, the bigger the transfer of oxygen was during the competition. Let's leave it at that for now, and we'll pick it up in the next video.